Good morning. So let us see today how to represent the shift operations using VHDL. Okay. So in last class we have seen what is register, what is shift register, what are the different types of shift registers, like that. Okay. So what is a register? Register is a group of flip-flops which is used to store more than one bit binary numbers. Shift register means the data which is there in the shift register can be shifted towards right hand side direction, left hand side direction, or right shift left circulate, left shift circulate, like that operations we can do on the registers. That's why they are named as shift registers. And we have four types of shift registers. They are named as shift serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out shift registers. Okay, four categories of shift registers we have. And now how to represent each shift register in the VHDL. Okay, so first of all I am going to represent here serial in, parallel out shift register. Okay, so for every VHDL representation case, first of all you need to write down the library IEEE. Okay, first one is library IEEE. After that, use IEEE dot use IEEE dot standard logic 1164. Okay, so these two statements are compulsory while writing the VHDL representation for any digital circuit. Okay, so library IEEE semicolon use IEEE dot standard logic 1164 dot all semicolon. Okay, that is IEEE is the standard library that you have to open. From that library, the package standard logic 1164 has to be selected, and also all the declarations of the package will be in the open mode for this program. Okay, that is the dot all. After entity declaration, so the entity declaration includes, or as per the syntax, it starts with the word entity followed by the word entity, name of the entity is user defined word or the user defined name. Okay, whatever the name you can use here. So here I have given the name as SIPO shift register, that means serial in, parallel out shift register is. This is the first line as per the syntax of entity declaration. So entity serial in, parallel out shift register is. Then port. So the port includes all inputs and also outputs. So in shift serial in, parallel out case, what are the different inputs? X input and clock input. These are the two inputs. X is the data input. It passes one bit binary value into the register, and all the elements of the register uses the clock signal for getting the synchronous operation. So X and clock are the inputs to the shift register, whereas Q is the output of the shift register. But since it is a parallel out model, all the bits of the register can be represented or can be extracted through Q output. So therefore, in this example, I have taken 4-bit serial in, parallel out shift register. That's why the Q is in the size of 4 bits. Okay. So see here in the port, X is in standard logic, clock also in standard logic, because these two are the 1 bit, whereas Q acts as a in out. Okay, in out. Data type is standard logic vector of 0 to 3, and initially the value in the register is all zeros. Okay, so before going to applying the clock signals, the value is all zeros, let us suppose. Okay, so that all zeros value is placed in the register by assigning symbol colon equal in the declaration itself. Okay, so after that, closing bracket of the port and semicolon, and finally closing the entity with entity name, that is serial in, parallel out shift register. Clear? The syntax of entity declaration of serial in, parallel out shift register is like this. Okay, so input is only 1 bit, Input is only 1 bit declaration, but whereas output consists more than 1 bit, that the number of bits equal to the size of the shift register, that the output is in the in-out mode. Why? Because the output of one flip-flop acts as the input for the another flip-flop. So that's why here the Q is declared as in the in-out mode. Okay, so here Q of 0 is the MSB bit and Q of 3 is the LSB bit, because the declaration is 0 to 3. Q of 0 is the MSB position bit and Q of 3 represents the LSB position bit. And initially the register consists, as per this program, all zeros. But I have taken one example to represent the shift operation in the serial in parallel out case. In that example I have taken the value of 0 1 1 0 that you can see in the following slide. Okay, that to what type of shifting operation here I am going to represent is a right shift operation here I am going to represent. Okay, so let us see the operation first of all. Okay, so see the register data can be represented with the letter Q. So Q of 0 is the MSB position, Q of 3 is the LSB position bit. So Q of 0, Q of 1, Q of 2, Q of 3 are the 4 bits of the shift register, and initially my assumption is it consists the data is like 0 1 1 0 0 1 1 0. Okay, so after that for the first clock pulse, what is the data of this register? Okay, since it shows the right shifting operation and that to one bit it shifts towards right hand side direction for each clock pulse. Okay, that is after applying the clock signal, the data of the shift register is moves one bit in the right hand side direction and the MSB position occupied with the X. Okay, so that is represented like this. The MSB position Q of 0 is X1, maybe X value with the first clock pulse, and this previous 0 is occupies Q of 1, means Q of 0 occupies Q of 1, previous Q of 1 occupies Q of 2, previous Q of 2 occupies Q of 3. So X1 0 1 1, that is the present data of the register. Then if you apply the next clock pulse, okay, so what will happen? Again the shift register data move towards right hand side direction by 1 bit. Okay, so therefore the MSB position, that is Q of 0 with new x value say x2, new x value say x2, Q of 0 occupies Q of 1, Q of 1 occupies Q of 2, Q of 2 occupies Q of 3. Therefore the register data is x2, x1, 0, 1, isn't it? Okay, similarly for next clock pulse with movement of 1 bit towards right hand side direction, the new data is like this. Like that the data will be entered into the register by 1 bit for each clock pulse, but the data you can extract from the register all the bits at a time, since the Q is declared in the form of vector. Okay, so therefore always the output shows the 4 flip-flops value of the register. Okay, so now how these operations can be represented in the architecture body, now I am going to show it is here architecture. As per the syntax of the architecture, it starts with the word architecture, behavioral of the name of the entity, that is serial in parallel shift register is, then begin. So okay, architecture behavioral of serial in parallel shift register is begin. Okay, then now since the model is behavioral model, the architecture statement is process, right? Process of clock, because the register is a synchronous register and all the event happens in the register should be aligned with the clock signal. Okay, so that's why process of clock, then process begin. Now the right shifting operation represented the clock of rising edge, okay. So only during the rising edge only the shifting operation can be affected, otherwise no. So for that one, if rising edge of the clock is then, that is if the rising edge of clock is happen, then only the shifting is like this: q of 1 down to 3, q of 1 down to 3. What is q of 1 down to 3? The present q of 1 down to 3 is previous q of 0 to 2, right? Isn't it? The present q of 1 down to 3 is equal to the previous q of 0 to 2, right? So that's why the assignment is like q of 1 to 3 equal to q of 0 to 2. So 1 to 3 is equal to q of 0 to 2, okay. And what is q of 0 value? Q of 0 value is x, right? So therefore q of 0 equal to x, okay. So for every rising case, for every positive edge triggering case, okay, or rising case, these two statements will be executed so that the value of register move towards right hand side direction by 1 bit position, and for every moment the MSB position will be vacant, that is filled with the x value, that is filled with the new x value or new x bit value, okay. So finally end if, after that end process, end architecture name, clear? So if you observe here, if you observe as per this operation, okay, the q of 1 to 3, q of 1 to 3 always is equal to q of 0 to 2, okay, because one bit is moved towards to the right hand side direction. Therefore from this table we can observe that what will happen, for every clock pulse the q of 1 to 3 is equal to q of 0 to 2, whereas q of 0 is filled with new x bit, the new value of the x or new bit of the x, always for every clock pulse. See here x1, here x2, here x3, here x4, like that for every clock pulse the new x value will be loaded into q of 0 location, whereas q of 1 to 3 is equal to q of 0 to 2. So like that the right shifting operation we can show. To represent this, the statements are like this: q of 1 to 3 is equal to q of 0 to 2 and q of 0 equal to x, okay. So similarly you write the program for other shifting operations, right? Is it clear all of you? Okay, first of all we need to declare entity as per the program. The entity you have to declare, you know, the entity includes all inputs and outputs, here inputs are data input is x and clock input is clock, okay. Since the model is parallel out, all the bits has to be extracted from the register simultaneously. So therefore q is declared in the form of vector consisting the size of 4, that is 0 to 3, and here in the program the initial value given, this is the program actually I copied from the textbook, that is the value is 0001, but while showing the example I included the value, initial value as 0110. Better you write that one here, because that is the example we have taken, that you write here, okay. So this is the entity declaration. After that, coming to architecture body, in the architecture body we have represented the VHDL in the behavioral model. That's why the entire action represented in the process statement and the process of clock we have taken, because it is a synchronous register. So with reference to clock, all the operations can be done in the register, that too for the positive rising edge of the clock, okay. So since the operations are right shifting operation by 1 bit, so the statements are q of 1 to 3 is equal to q of 0 to 2, and q of 0 always the new bit of the x value. Okay, the value of the x, whatever the value of the x, that is loaded in the q of 0. So end if, end process, end architecture name. Okay, thank you.